Here we go. So today is taking a look at the first 4 chapters, doing some review type problems. There will be a little bit of time when I'll pause where you'll have a chance to kind of let some things soak in a bit. This is being recorded, so you don't have to be copying this down with copious notes. There's going to be a lot of writing on the board, so it's not going to be beneficial to just write everything down that's going up there. However, as we're prepping and doing this, thinking about wherever you keep your notes, you can, but primarily you're thinking of questions that you're going to have to ask as you process information, because I know not everybody processes at the same speed. There'll be time to then take and ask those questions as we get there. Nope. So here we go. First thing I did in preparation for you was I sat down and thought, okay, chapter 1, what were some of the key concepts that are here? So I don't know your strategy for studying for things, but generally speaking, what I would recommend is you start out by brainstorming all the things that you remember and writing those things down and then adding things in. This is just a small list of some of the chapter 1 ideas, but they're some of the bigger ones that we've talked about, such as sampling. Now, when you're doing sampling, ideally, what you want it to be is you want it to be representative. All right, so think for a minute about what representative means, and then share that with the person sitting next to you. Yeah, so ideally, the sample should be a pared down but accurate reflection of the whole population. So for it to be representative, there should be similar qualities in the sample that are in the population. What's that? Yeah, the outcome, the results, the data that you collect theoretically will be like a microcosm of the entire population. The hard part is you don't know. If you do a really good sample, a really good random sample, you won't know if it actually does represent the whole population because you can't look at the whole population. But then certain limitations exist to say, well, you can't just keep sampling hundreds and hundreds and hundreds of people in hopes that you'll get something big enough. You just have to go as a statistician and say, I used good procedure. If I use good procedure, then I have to assume that my sample is a good representative sample. And by good means a lot of things, but it's representative. It's going to hopefully mirror what the whole population says. Is it possible that I can get a very skewed data set in terms of skewed away from what the actual population is? Sure. In which case it would be a high bias scenario away from what we actually think it should be, but not bias in terms of the types of bias we'll talk about down here. All right? And then we talked about different types of sampling. Cluster sampling, simple random sampling, systematic sampling, and stratified sampling. Those are kind of the top 4 in terms of types. The ideal is SRS. It's always a simple random sample. That is, everybody in the population has an equally likely chance of getting selected, and they're all independent of one another. And then we talked about things like knowing our population, and certain values of the population are called parameters. If we knew the population average age, that's a parameter. If I take a sample and find the average age of my sample, that's a statistic. So here we used letters that typically were Greek letters. We use the Greek letter mu to represent, and that means the average of the population. We had sigma squared, lowercase sigma. That's the population variance. Sigma is the population standard deviation. And they are related. Sometimes people think, wait, are they separate? No, if you just take the square root of this, you'll get that. All right. And then in a sample, if I do a sample average, that's x bar. The sample variance is s squared. Sample standard deviation is s. Those are the most common parameters and statistics that we're going to use. There are others that are out there, but those are fairly universal amongst all statistics books as well. You might get a place where it gives you, when we're talking about like a population proportion, so a proportion would be like how many people out of the total, and that would be my population proportion. Usually they would use capital pi and then lowercase p, or possibly p hat. P hat is the one that we'll be using. We're not going to typically use pi, but instead we would just call it lowercase p without the hat. So the p would be population proportion, p hat would be a sample statistic. All right, so then those are things going on. Okay, moving on. Sample bias and error. Sampling bias, that means that something happened that's creating some type of a bias. And then we got to think of all the different types of biases that we've talked about. We've talked about like oversampling bias, where I've maybe talked to too many people that are too similar within a population. So maybe I didn't have a great technique. And so my response is going to more heavily be influenced by those people's responses. Sampling, other biases. Response bias. You talk to someone and ask them what they think about some opinion, and they lie to you. That's a bias. Why would they lie to you? A lot of different reasons why people lie. We're not going to go into all of those, or any of them really. But there's nothing you can do as a statistician doing sampling that's going to change and make people not lie. All right? You try to do anonymous ones, they might still lie. All right? So you got oversampling, undersampling. They might lie. I've talked about like just how you word questions can influence how people respond. So those are like wording biases. And then sampling error, this is the one I said where it's not actually wrong. It's just that it's not exactly consistent. So anytime you do a sample, my sample average, X bar, will not equal mu. If it did, that's really, really, really rare. Your sample statistic will approximate mu, but it won't equal mu. And the difference between them is called error. And that's an okay thing. It's a normal thing. Again, if I'm using good procedure, I am okay with the difference between those two. And then there are certain things that we can do to decrease error. If you sample more people, theoretically, my X bar should get closer to my mu. All right? If you want to know a better idea, well, let's just sample more. Which, that's ideal, but in a real world scenario, it costs money. So if you're ever working with a statistician, whether you're the statistician or you're getting feedback from a statistician, they're going to say, obviously we could get better results here if I could sample more people, do more things. And then your boss, or you, if you're the boss, says, yeah, we don't have the money for that. So we're going to do the smallest possible sample to get me the best results that I'm okay with being this far off, which is called error. All right. And we've hit this one quite a bit, quantitative versus qualitative. You should be very familiar with that. Quantitative means measurable. Qualitative is a quality or a category. We've got designed experiments. I got their three basic components: randomization, replication, and control. And within that, you have treatments. A placebo is a treatment, even though it's a fake treatment. With people, sometimes you give them fake treatments to think they're getting something. And then they might positively respond. And if they positively respond, we call that the placebo effect. All right. There should be a comma between there. And then we got the different variables that are happening. We have explanatory variables and response variables. Variables are the things, I always think variables means they change. How are they changing? What's changing? All right. Blinding. If you don't know if you're getting a treatment or a placebo, am I getting the actual medication or am I getting a placebo? If you don't know, it's called blind. It's a blind experiment. If the person administering it and the person receiving it both don't know, that's double blind, and that's better. So that way the only person that knows what's going on is the statistician who's designed this thing in some back room somewhere, and everything is barcoded, and it goes out and comes back. Paired, this was a struggle that some people were having, I think, on that online quiz too, which, yes, you can still do that again. Paired is, one example of pairing that's like pretty straightforward is I give you one medication, and then I see how you respond to it, and then 2 weeks later I give you a different medication, and then see how you respond to it. And it's paired in the fact that you get both of them, and we assume that you don't change. All right? So it's with the same, as many of the variables reduced as possible. So if I can say that, the other way to do a paired thing would be looking at a big set of data and look at 2 individuals and say, try to match them up as closely as you can. So 2 people of the same gender, about the same age, the same habits, lifestyle, diet, etc., as much as we can eliminate and say they are as close to the same as possible, and then we'll give one of them one medication, the other one the other one, and then see how they respond. Like if we had like a whole plethora of twins out there, that would be awesome for medical experiments. One gets one gets the other, because you would assume that identical twins, I'm talking not fraternal, identical twins would have the same identical basic structure, so you could see, does one change versus the other one change? So that's paired. Another pairing I've seen, and it's interesting if you think about it this way, but you take married couples and you assume they have something in common, and then you run a test on the men of the married couples and the women on the married couples and compare differences, as opposed to just single folks. And then whatever you might be studying. So in that one, when you're looking at just the married people, that might be considered paired. It would be a very unique way, you have to phrase it to set it up in order to be considered paired. If it's not paired, then you're just going to take, 100 people, we're going to randomly assign them to a group of 50 here and a group of 50 there. And then the 150 gets the medication, the other one gets the placebo, and then we compare the results. And we hope, because of randomization, that they are going to be similar representations of the population. Paired or not. And then biases. Oh, we already talked about that a little bit. So let that sink in for a moment. And then don't forget, too, designed experiments. Ultimately, the reason why we do designed experiments is to prove causation. You're not going to get a bigger hint than that. All right. If it's not a designed experiment, if there's not randomization, if there's not replication, or there's not control, it might be an experiment, but it's not going to be a well-designed experiment. If one of these three things is missing or done poorly, causation cannot happen. Then we're only looking at an association. I was listening to a podcast talking about brains and structures of brains, looking at Einstein's brain. And now I'm trying to remember the name of in your brain, if anybody knows your brain structure, there is a fissure, it's a big kind of ridge but it goes into your brain. It's like a fold. But there's a prominent one in your brain that in Einstein's brain, it was not that prominent. And they think that might be why he was ability to connect things so much quicker, is because the brain, the transmission didn't have to take so far to get around it. They did a lot of experiments on it, but ultimately they're just looking at association. Is there an association between this and that? And they don't know. All right, so they don't know if it's cause effect. They don't know that having a brain structure like this actually makes you smarter or not. They're just saying, hey, looks like his brain and a couple other brains that they've looked at of people who tested as geniuses when they were alive. They look at them after they're dead and they all seem to have these similar things that all these other brains don't. That does not make it cause effect. That just means they've observed something interesting. All right, but then you'd also have to be able to do some functional MRIs of people's brain to find out, is my brain like that or is my brain not like that? Chapter 2. Hit on these here quick. Quantitative graphs, box plot, histogram, stem plot, frequency polygon. There's others. Those are some of the ones that we talked about. Frequency polygon, this is where if you have something that's like time series data, so across the x-axis is time, and then the y-axis things is happening, and it's going up or down like this, and then you connect the dots, and it looks like a jaggedy ridge. That'd be a frequency polygon. Qualitative graphs, pie chart, bar chart. Pareto, there should be an O right there. Pareto is a bar chart that's either in descending or ascending order. So whatever, find out the hair color. The highest hair color would be the first bar, then the next bar would be the next one, and then going down to the bottom one. That's a Pareto chart is just a fancy name for a type of bar chart. We talked about centers, mean, median, and mode, average, 50th percentile, most commonly occurring. All right. And then when we were describing graphs, we talked about shapes of graphs. Is it uniform? Same throughout? Is it modal? Is there one pronounced area that's more than the other? Is it skewed left or right? And we'll just do a quick graph drawing. So this graph right there is we'll assume that is right skewed. Oh, that's terrible. That would be a left skewed graph because the tail is getting pulled to the left, so left skewed. Which also means that the mean in a left skewed graph is less than the median. Might be only a little less. This one, the mean is probably significantly more than the median. Maybe it's symmetric, maybe it's not. Those are different ways that we've used to describe shapes of graphs. If there's two pronounced mounds to it, like we had in our last time that we gathered, I did a data and we looked at weights of Chiefs, Kansas City Chiefs, weights of San Francisco 49ers. They were bimodal, all right? So you can go back and watch that video if you forgot that one. And then spread, variance and standard deviation. Variance being the average squared difference of every data point, and then this is the average distance of every data point from the mean, standard deviation. Talked about outliers and calculating them, usually with a box plot. Know the calculations and how to do that. We didn't talk much about outliers with the Gaussian curve, the bell-shaped curve, but we will. We're going to actually spend a lot of time on the bell curve soon, but not quite yet. But knowing the empirical rule that if data follows a bell-shaped curve, also called a normal curve. If data follows a normal curve, the mean is in the middle, 1, 2, 3. That's 3 sigma up, and then 1, 2, 3. That's 3 sigma down. Within that interval, plus or minus 3 sigma, 99.7% of the data occurs. Within 2 standard deviations of the mean, from there, that's 2 sigma up, because mu plus 1 sigma plus 2 sigma. Mu 1 sigma down, 2 sigma down. So in that interval, we would expect 95% of the data to occur. And it's not technically an outlier, but that's what a lot of people normally think of when they think, like, because you only have a 2.5% chance of being up here. You only have a 2.5% chance of being down there, which typically makes you unusual. If you're in the top 2.5% or bottom 2.5%, that'd be unusual. If you're in above 3 sigma, you're rare. Below 3 sigma, you're rare. Things that occur that are bell-shaped, like IQ scores, go back to Einstein for a second. If you've ever taken an actual IQ test, the average of most IQ tests are 100. Standard deviation is usually 10. Sometimes it's 15. So that'd be 110, 120, 130. And then anything above 130, that used to be the designation for genius. All right. Once you get over like 190 for a IQ, they actually have to give you a different IQ test because you can't measure it with this IQ test. With a standard IQ test, IQ's that high. And this is how, if any of you, let's see. So it used to be that the IQ test also determined who got special needs help in school. And if you're below 2 standard deviations, you qualified with a learning disability in some area. And that's how that used to be determined. It's slightly different now. But the bell curve, and then some of you ask your professors if they grade on a curve. And so I'm going to tell you what that actually means because most, I think, professors also have it wrong. If I'm in here, that's a C. This is a B. That's an A. This is a D. That's an F. If you grade on a curve, you have to have about 5% of your people get Fs. 5% get As, and that's it. I mean, they might adjust those slightly, and then most people get Cs. That's grading on a curve. I don't think I know anybody who actually grades on a curve, regardless of what you get. If you're in the top, the way I have it drawn here, you're top 2.5%. If this is above, so this is 2.5% up here. If that were really true, if the average grade in the class was an 85, that's a C. And you would all get C's that are in and around that. Only the top 2.5% would get an A. So that's actually grading on a curve. I think what most people do and a lot of professors do is they just move things, they adjust things, they reset it out of a different amount. That's not grading on a curve, that's just a linear adjustment. That's just one of my many pet peeves about how people misuse statistics language. All right, chapter 3 talked about some of the basics of probability, like if you think of all the possible outcomes and add up all their probabilities, it equals 1. The smallest any probability can be is 0. The highest it can be is 1. If it's 0, then it can't happen. If the probability is 1, that means it will happen. We did an example in class where we worked through experimental probabilities versus theoretical probabilities, right? Experimental probability of getting a certain number of diamonds in a random sample of 10 cards versus the theoretical, which would be then us, like what it should be or should follow. Know the difference between these. Sample space lists all the outcomes. All the different outcomes could be like this. An outcome is a singular event. An event is a set of outcomes. So, for example, I draw a card. My sample space, if I draw a card from a deck of cards, my sample space would include 52 different possible things that could happen. One for every card that has. So 8 of diamonds is an outcome. So the sample space lists all the outcomes. Then if I decide to take and say diamonds, well, that's an event because it takes 13 of these outcomes and clumps them into one event. Mutually exclusive, we talked about this, did a quick little probability on it, but mutually exclusive means two things that can't happen at the same time. Draw a card from a deck. What's the likelihood that it's a diamond and a spade? Like, wait a second. No diamonds are spades. Spades aren't diamonds. They're two things that have nothing in common. They are mutually exclusive. If you're going to draw a Venn diagram, spades, diamonds. There's no intersection. You have no card that's in both suits at the same time. They are called mutually exclusive. Not the same as independent. Independent means knowing the outcome of one event does not change the probability of another event. If we knew a card was a diamond, the probability of a face card is the same as if it were the probability of a face card in the entire deck. Again, we covered that. We did that one in class one time. So independent means, from a formula point of view, if the probability of A given B is the same as probability of A, in other words, if I know B and find the probability of A is the same as probability of A all by itself, they are independent events. That's how you would prove independence. Probability formulas. And you will have these on the exam. There will be a little sheet that has all the probabilities on it and other formulas that we have. But it's that. You have to know what it is and how to use it. Intersection means and. So if you're talking about two events that are both happening, probably A and B. In a Venn diagram, that would be, now I need to have an intersection. And if I go that area right there, I need another variable. Spades, diamonds, we'll call this F for face cards. If F is that for face cards, then this intersection right here are all the cards that are face cards and diamonds. So intersection would be and, a card that's a face card and a diamond. And then we had our other formula, which was this, probability of A union B, or in English we say A or B, is probability of A, plus probability of B, minus the probability of both A and B. Ooh, got a little sloppy on the end there, sorry about that. But you get that. So that's the probability of union, or. And the time we covered that one in class, so we actually did like a table of values, and we looked at where is this row and that column. That was the intersection. Then we said this row or that column, which are the two, like the row and the column added up. And when you did that, you added the intersection an extra time, so we got to subtract it away once. And then complements. It's either an event or not the event. So if I have event A, and I have the event probability of A complement, those two add up to 1 because you're either in it or you're not. So A and A complement, when you have two things, and again, that's all it is. I'm either in A or I'm not in A. Those are the only two possibilities, which means when I take the probability of each and add them up, it adds up to 1 because it's every possibility. You're either in A or not in A. So if I'm looking at my diagram over here, if I look for D complement, that's everything that's not in D. So I'd go like this. Okay, this is not in D. This is not in D. This is not. Anything that's not in D would be shaded. So diamonds, 13 out of 52. Everything that's not a diamond, 39 out of 52. And then our most recent. So yes, we're not doing chapter 5 on this exam. It did say on the syllabus 1 through 4. I am consistent. We did start chapter 5 a little bit, but I don't want to test on it until we've completed the rest of chapter 5. So this will be the end of what we have for full content, and then we'll go into some example problems here in a minute. But these were the 4 different distributions that we did in chapter 4. The binomial, sometimes called the Bernoulli, because it's named after the guy who came up with it. Then we had the geometric, the hypergeometric, and the Poisson. Here's the question that I want you to start with. You're going to turn to your partner, maybe reference back to some notes. See if you can figure out all those nuggets of information. Insert it into your table to help you kind of process through and figure out which one's which. And then we'll go through some examples in a minute. So turn and talk. Questions on that? All right, so get that again. So Ali was 77. Oh, this was 80. I did the wrong number. Dang it. So 80 is here. This number should be 80. That's what I get for going too fast. This number is 80, so this is, again, 80 says be 90, 100, 110, 3 standard deviations up. Ali was right down here at a 77. Which is 3 below 80. And in terms of, it's 3 out of 10, 3/10 of a standard deviation below. This person is 0.7 out of, or 2.85. 2.85 is 0.15 out of 0.7 below. Harder to see what that is, but that would be 15 out of 70. How does that compare to that? And that'll tell you who's relatively in a different position. I really messed up my presentation on that one. I'll try to go back and get you a better idea of that after class. I'll create a new slide. I'll add that on before I upload this tonight. All right. Things like this, identify the population, sample, parameter, statistic, variable, data. If you've been doing the check your understanding problems, you've been like, oh, we did so many of these. It should not be a hard challenge to be looking at and saying, so if I look at this one, the insurance companies are interested in the mean health costs each year of their clients so they can determine the cost of health insurance. Who's the population? The population are all of this insurance company's clients. What is the sample? That would be whoever they decide to choose out of their group of people that are their clients and looking at mean health costs. But the sample would be whoever they choose. There wasn't one given here. So you'd have to say, well, it would be sampling from their clients somehow at random. The parameter would be the average health cost of all their clients in 1 year. The statistic would be the average health cost in 1 year for the sample of clients that they haven't chosen yet. What's the variable? What changes? Cost. Health costs are going to change. And then the data would be, I don't know, pick numbers. There isn't anything given necessarily here, but that would be how much you're spending in one given year on health costs. These are, I'm not going to read through all of this. You can hit pause and read through this when you're prepping for the exam as well, but we'll pick one of these. It says, name the sampling method used. So let's look at this one. Librarian at a public library wants to determine the proportion of the library users are children. The librarian has a tally sheet on which she marks whether books are checked out by an adult or a child. She records this data for every 4th patron who checks the book. Well, that would be stratified. Not stratified, that would be systematic, because her system is every 4th person. A teacher wants to know if her students are doing homework, so she randomly selects 2 rows. Randomly, that's good. 2 rows, and then calls on all the students in those 2 rows. Well, that's cluster. Because every row is a cluster, and she randomly selects a couple clusters and then samples everybody in that cluster. knowing how to calculate probabilities. So if we take this scenario, it says among 18 to 39-year-olds in California, this was a while ago, like 10 years ago, Prop 8, they found that the approval rating for that was 78%. So C, California registered voters, those who support same-sex marriage, this was then 78%. And then it'll define things like this. What is this going to be? What is this going to be? What will each of these be? Describing this in words. And, union. So and or, using the two formulas that we have to be able to prove and show those probabilities. So what I'll do is, again, before I go back and upload this, I'm going to go back and insert these numbers in so you can try this on your own. All right, so when you're watching this or rewatching this video, you're going to hit pause and work these problems as you read through the stuff and then see if you're getting the right answers. If you're not, check with someone else that's in class, see if they're getting the right answers. If y'all are not getting the right answers, then that's where you shoot me an email, stop in and see me, which I'm not really around, but I am. Wednesday, I plan on being on campus 8. I'll be in the B and C from 8 until class starts. That's just kind of my normal procedure on Mondays and Wednesdays. And then, that is my last slide for that one. So I'll be adding a slide to correct myself when you're talking about your relative position based on your score versus your standard deviation. Because just, you can think about this in a lot of ways. Just because two people have the same score doesn't mean they were relatively speaking the same position as someone else. It all depends on what the average was, what the standard deviation was. If the standard deviation is really, really small and you're really, really close to the mean, that might be worse than the other way where it's a larger standard deviation, but you're further away. So it's all relative position to where you're at. So this is the first part here. 61% of California registered approve of same-sex. That's this one, because that's how this phrase goes. B, voters who say that the Supreme Court's decision is somewhat important. It says 6 in 10 California registered voters said the upcoming ruling was important to them. So that's the 0.6. This number up here says among 18 to 29-year-olds, the approval rating of what? So out of these, so given that they're this, 78% approve of C. So this is given A. What's the probability of C? C is those that approve same-sex. So of these, that's the percent. So that's how that gets translated. And then down here it says, out of those registered voters who support same-sex marriage, so that's out of C, or given C, 75% say the ruling's important. So C given B. B given C. That's the 75%. A is not immediately available. Describe C given A in words. So that is out of the 18 to 29-year-old registered voters in California. So this is my given out of these people. This is those who are supporters of same-sex marriage. All right, if it were a probability, then I'd say the probability of that happening. C and B, that's the intersection. C times B given C, that's just straight formula. This was already determined. The 0.75 was B given C. That was already determined. Multiply to this number. C or B, that is California registered voters who support same-sex marriage, or say that the ruling is important to them, will be the two added up, which includes the intersection. If you think about a Venn diagram, if we did 2 in this Venn diagram, we're going to have C and B. Or means I'm in one, or the other one. And what you notice is this part right here in the middle got counted twice, which is why we have to subtract it away once. And that came from the previous problem. And then lastly, you're going to have A happening somewhere in here as well. And you could plug some of these in, but this is not going to be easy to find. So I wouldn't worry about that right now. And then here's the last thing I promised that I would do. So just getting at that idea, who's better? when you're comparing two different things, like a score of 18 and a score of 100 for A and B, like if A score is 18 and B score is 100, that doesn't mean anything unless you know how they compare to their averages. So here we see that X scored better than the average because the average mu is 12. Well, 100 is also better than 86. So they're both better than average, but the question is how much better than average? That's where the standard deviation comes into place. So if we see this, 18 into 12, so we have a score that's 6 over. So it's 6 more than the average. And over here we say, well, this person scored 14 greater than the average because 100 is 14 more than 86. And still you say, okay, well, this is still more than that, but relative to the spread of the data, how is it? Because here the average data only varies by 4. Here the average data spreads by 10, which means this has a greater spread, but relative to the difference, how does that compare? So what you would do is, basically, I'm 6 more, but I'm like, this is 1 standard deviation. Well, how many standard deviations is this? Up. So if I divide that by 4, I'm going to have, let's see, it goes in there, 1.5. So this number here is 1.5 standard deviations above the mean. Well, how about this one? Well, divided by 10, that's 1.4. So 100 is 1.4 standard deviations above the mean. Since this is more standard deviations above the mean, that means this is relative to their group a better score. So while this obviously is a much smaller number than this one relative to what's going on with the averages and the standard deviation of whatever class or program or whatever's happening here, this score relative to the rest of the class is more standard deviations above the mean than this one is for this particular class, which means this person A, did better. So person A did better because they were more standard deviations above the mean. And of course I support it with calculations and then explanation as well as I write it down. You wouldn't just say A. You'd have to support it with numbers, calculations, and then explanations of, since A was 1.5 standard deviations higher and B was only 1.4 standard deviations higher, that makes the A score better. There you go.